Yeah, for those of you who just joined, we'll wait a couple more minutes until the number of audience sort of stabilizes. Um, and so Hongyi, do you want to answer questions in the middle of the talk, or do you want to do it at the end?
I think I can do it in the end.
Okay, okay.
So, yes,
Yeah, so if
because
people
the
have...
talk is kind of short, so I think I can do it in the end of the talk.
Okay, okay, yeah. So if people have questions, hold on to it until the very end. And you can also type the question in the chat, and Hongyi will pick it up at the end of the talk. All right, I guess we can start. So welcome everyone to MLSLP 2021. This is like this marks the 10 years of me attending MLSLP. So the first time I attended MLSLP is actually 10 years back. I can't believe time flies. And back then, we don't even have deep learning, and now deep learning is everywhere. And we're doing crazy stuff right now. And yeah, so this is a place where the ML people meet the speech people, and then the speech people meet the ML people. And at some point, we feel like ML is so prevalent right now in speech. Why would we even need to have MLSLP anymore? But it seems like given the current interest in self-supervised and unsupervised learning, I think we just need more of the interaction between ML and speech. And so I'm very glad that I'm actually hosting this workshop 10 years later. And so hopefully I can bring the enthusiasm I learned back then when I first attended. And hopefully you can enjoy that as well. And okay, so for the first talk, we're glad to have Hongyi Li from National Taiwan University. I don't even need to look at the bio in order to introduce Hongyi because we were colleagues back in master's. So Hongyi graduated from National Taiwan University. I believe it's almost like 10 years ago. Yeah. So he obtained his master's 10 years ago, and then obtained his PhD afterwards. And then he was a visiting scholar at MIT CSAIL, and then now I believe you're an associate professor there, right?
Yes.
Yeah,
Yes.
and he has done a lot of work in speech, and so now he's going to talk about self-supervised learning and what he has learned along the way. So yeah, Hongyi, the floor is yours now.
Okay. Thanks, Hao, for the nice introduction. And Hao's opening just remind me that I think I also have attended the first workshop. So I also attended the same workshop 10 years before. So it's very nice. It's my great pleasure to be here again. So I'm Hongyi Li, and this slide is prepared with my PhD student, Leo. And in this talk, I'm going to ask and answer one question: is self-supervised learning universal in speech processing tasks? So what is self-supervised learning? In the following talks, you will find out lots of people are talking about self-supervised learning. There are several talks focused on self-supervised learning. But because this is the first talk of this workshop, I think I can take the privilege to introduce self-supervised learning to the audience a little bit. So in self-supervised learning, the training has two phases. So you have two phases of training. So the phase one is pre-training. You have lots of unlabeled data. And with those unlabeled data, you can train an upstream model. You can train a self-supervised model. So to be simplified, to make the long story short, what upstream model can do is it takes speech signal as input and output a sequence of representation, output a sequence of vectors. And there are many different ways to train this kind of upstream model in an unsupervised way. I'm not going to go through the details here because there are lots of talks will focus on how to train this kind of upstream model. So you will learn different way to train this upstream model later. So I'm not going to talk about other speakers, what other speakers were going to say. So you just know that with lots of unlabeled data, you can have an upstream model, take speech signal as input and output representation. And this is something I have to emphasize. Those upstream models, they are trained in a task agnostic way. That is, when we train those upstream models, we do not know what is the downstream task. So we do not know this upstream model will be used in ASR or speaker recognition. We do not have this kind of information when we are in the phase one, when we do pre-training. And there are already lots of self-supervised model. There are already lots of well-known stream model, upstream model, for example, PASS, APC, MPC, Mockingjay, the Cora series, Web2Vec series, and Hilbert series. I'm not going to introduce how those model is obtained, but in this talk, we are going to compare the performance of those models on a wide range of different tasks. And in phase two, we are going to use this model in a downstream task. So we have a downstream task we want to solve, for example, ASR or speaker recognition. Then you have a little bit label data for a specific task. Then you put an downstream model on top of the upstream model. So your downstream model will take the output of the upstream model as the input and output something. If you are considered speech recognition, then the output of the downstream model will be the transcription. And you will use this little label data to train the upstream model. And sometimes you will also use those label data to fine-tune the upstream model. But I put a dotted line here to show you that this fine-tuning is an optional. It is unnecessary to do the fine-tuning here. So this is the basic idea of self-supervised learning. Now here comes the question. We already have a large amount of self-supervised model. And in the paper, usually the paper show that they achieve good performance on speech recognition. But how about other tasks? Are those models specialists for ASR, or they are universal, or they can be used in other speech-related tasks? To be more specific, what I mean is those models, those upstream models, has been shown to achieve good performance on ASR. So you can add a downstream model and fine-tune the downstream model and the upstream model, then you get good performance in speech recognition. But how about other tasks? How about other tasks which is very different from speech recognition? For example, speech identification. So in speech identification, if you have a little bit label data, can you also train another downstream model which get good performance on speaker identification? Can speaker identification also leverage the same upstream model, which achieve good performance on speech recognition? So if you asked me this question 1 year before, my answer would be those upstream models may not be universal. They are probably specialists. Because if a model is good at ASR, that means the model learned to extract content information and probably it learned to ignore the speaker information. So if a model is good at speech recognition, that means it ignored the speaker information. So it might have poor performance on speaker-related tasks like speaker identification or speaker verification. So you cannot eat your cake. You cannot have your cake and eat it at the same time. So a model is good at speech recognition, probably it will not work well on speaker recognition. So probably those models are just specialists. But this is just some speech without proof. So I want to do some experiment to verify this hypothesis, to see this model is specialist or universal. So here we have a project called SUPERB, a speech processing universal performance benchmark. And the team member of SUPERB from lots of different institutes, including National Taiwan University, CNU, NIT, Johns Hopkins, and Facebook AI. And we have a publication in this interspeech. And here are the team members. So we cannot have this project without those excellent researchers and students. So the basic idea of SUPERB is we already have lots of self-supervised models. And we are going to use those self-supervised model on a wide range of different speech processing tasks. Not just ASR, we are going to apply that on many different tasks. So you can consider this as the decazone of the self-supervised speech models. And here is the introduction of our contestants. So this is the model we are going to compare, and they have very different network architecture. Some of them are very shallow, some of them are pretty deep, and they have very different parameters. Some of them are small and some of them are giant, and different stride, different input feature. And most of them are trained from LibriSpeech and LibriLite, but using different amount of data. And something interesting here is about their pre-training methods. So I list their pre-training method here. So you can find that there are many different kinds of pre-training methods. So G here represents reconstruction from the input, and P here means token prediction, and C here means contrastive learning, and VQ here means the model have vector quantization in it, and F means the model will try to predict the future information, and N here means the model will mask the inputs. I'm not going to go through the detail here. I just want to show you that there are a wide variety of different approaches to train your model from the unlabeled data. And you will learn some of the approaches in the following talks. And here I'm going to introduce the task a little bit. This part will be very quick because I believe most of you are already familiar with those tasks. So we have some tasks related to content. We have phoneme recognition. We have keyword spotting, means given a segment of audio, the model have to do the classification, decide this audio segment belong to which keyword. And we have typical speech recognition. I do not have to introduce what is this. And we have query by example, that is given a long spoken document and a short spoken query. Model have to determine whether the short spoken query appear in the spoken document or not. So we have 4 tasks related to content, and we also have 3 tasks related to speaker. We have speaker identification. Given an utterance, model have to determine this utterance belong to which speaker. We have speaker verification. Given 2 utterances, the model have to determine these 2 utterances are uttered by the same speaker or not. And we have speaker diarization. In speaker diarization, given an audio archive, for example, a meeting recording, there are several speakers in the audio archive, and the machine have to determine which segment belong to which speakers. So this is speaker diarization. So besides content and speaker, we also have some tasks related to semantics. So we have intent classification. Given an utterance, the model have to determine the intent of the utterance. And we have slot filling. In slot filling, given utterance, the model have to extract the slot value of different slots. And those are spoken language understanding tasks. And typically, those tasks are solved by the concatenation of the speech recognition system and a text understanding system. But here, we are going to train those models end to end. So we do not have speech recognition system here. The model have to take speech signal as input and directly output the intent or directly output the slot values. So these models are trained end to end. We also have emotion recognition. So given occurrence, the model have to determine the occurrence belong to which emotion. We do not have time to go through the details of the corpus we use in each task. You can find more detail about the corpus in the paper. So this is the setup. So now we can start our game. Let's start the round one of the game. So in the round one, we have some very strict constraint to all the models. So in the following talks, I will just list 2 downstream models, but keep in mind that we have 10 different downstream models. We have 10 tasks, so 10 downstream models. I just list 2 here. So the constraint is, first, the upstream model is always fixed. We will not fine-tune the upstream model. We use the off-the-shelf upstream model. We use its original parameter. It will not be fine-tuned with the downstream tasks. And for each upstream model, we only extract its last layer output. So the downstream model will only take the output of the last layer from the upstream model. And because the upstream model is fixed, so all the downstream model actually use the same set of representations. And the network architecture for a downstream model is predefined. So it's fixed, it's predefined, it's the same for all the different upstream models. For example, for all the different upstream model, for in the ASR task, the downstream model is always 2-layer LSTM. And for speaker identification, the downstream model is always a linear layer. And here, I list the downstream model, the network architecture of the downstream model used in different tasks. So the basic idea of the network architecture of the downstream model is we want to make it as simple as possible. So if we can solve the task with linear layer, we just use the linear layer. But some tasks is more sophisticated. We cannot get reasonable result by linear layer, so we use some LSTM. But we try to keep the downstream model as simple as possible. So some people may ask, why give the upstream model so many constraints? Fine-tune the upstream model may give you better performance. We did try it. Of course, fine-tune the upstream model can obtain better performance. But here, what I want to show that is if we fix the upstream model, that is, we use the same upstream model across all the tasks, and we also limit the downstream model's capacity. And if the upstream model still obtain good performance on all the different tasks, that means the upstream model can extract the universal feature. So here we only have one upstream model, and it is used in all the different tasks. We do not fine-tune its parameter. If we can still obtain good performance in all the different tasks, means this set of feature is universal. If we have an universal feature, then in the future, if we want to build any new task related to speech, we can directly use this feature without fine-tuning the upstream model. We can directly use this feature in any new application. This sounds wonderful. But this sounds too good to be true. Can we really have a set of universal features that work well on all the different tasks? This doesn't sound realistic. So at the beginning, I think probably we cannot have universal feature. So all the model will perform very poor in the round one. But anyway, let's see the result of all the model in round one. So here is the result of the model, the self-supervised model on many different tasks. So we have 4 content-related tasks, 3 speaker-related tasks, 2 semantic-related tasks, and 1 emotion recognition task. And here the baseline is F-bank. And here are the result of different upstream models. And here we have the result of all the upstream model in all the different tasks. And this table is sophisticated. We have lots of different numbers, and actually different downstream models use different metrics to evaluate the performance. So I'm not going to go through the details in this table, and those numbers are very small, so it's probably difficult for you to look carefully about those numbers. But here I mask the result, which is worse than F-bank. So for the black box means the result here is worse than F-bank. That means the upstream model is not helpful here. And you can find that actually in several different tasks, self-supervised model is always better than FBank. In several different tasks, self-supervised model is always helpful, and it is helpful across many tasks. And but probably they do not have a very good performance on automatic speaker verification. It looks like they do not work well on ASV. And you may find that we do not show the result of Web2Vec 2.0 large and Hubert large here. And this is because these two models perform very poor in round one. So it looks like round one to put too much constraint on top of those self-supervised model. So we do not fully leverage the power of self-supervised model. Then we have round two. So in round two, we relax the constraint a little bit. The only constraint we relax is we let the downstream model pick the layer it wants. So the downstream model is not necessarily use the less layer output. It can use other layers. And other constraint is the same. We still fix the upstream model. We still keep the downstream model have the same network architecture, and then the network architecture should be as simple as possible. And this is how the downstream model pick which layer it want to use. So the parameter of the self-supervised model is always fixed, and each layer will output a sequence of representation. And we weighted sum each layer. We weighted sum the representation of each layer and obtain the final representation, which will be considered as the input of the downstream model. So each layer has a weight. So layer one have W1, layer two have weight 2, and so on. And let's consider the output of layer one is X1, the output of layer two is X2. Then we weighted sum the representation of all the layer and obtain the final representation. And the weighted sum, the result of weighted sum will be input of the downstream model. And those weights are jointly learned with the downstream model. So those weights can be considered as part of the downstream model. They are jointly learned with the downstream model. So you can consider those weights as how the downstream model will select each layer. So if some specific layer have larger weights, means downstream model think the representation of this layer is suitable for a specific task and decided to use that layer to solve the problem. So this is round two. Then let's see how good those model can achieve in the round two. So now we have some new member here. We add the result of Decor 2.0, and we also add the result of Web2Vec 2.0 large and Hubert large. So for the result worse than FBank, we put them in the black box. So you can find that there are only a few cases that the result of self-supervised learning is worse than FBank. So self-supervised learning outperforms FBank in most cases. And you can find that actually there are several models, they are all around. Some models can outperform FBank on all the 10 tasks. Here, NPC, Decora 2.0, Web2Vec series, and Hubert series, they can outperform FBank on the 10 different tasks. This shows us the output representation of those models can be universal. And here we do some analysis. So a question I want to ask is, we know that those tasks have some relationship. So those tasks are about content, those tasks are about speaker. So those tasks have some correlation. Does the performance also have the correlation? If a model obtains good performance on ASR, does that mean it also obtains good performance on phony recognition? And if a model is good at ASR, does that mean it will be poor in speaker identification and speaker verification? To answer this question, I compute the Spearman correlation between different tasks. So we just take the vector here, we just take the value here, and we compute their Spearman correlation to see whether some tasks have some performance correlation. And this is our result. And to our surprise, actually the task with similar characteristics, the task need to extract the probably the representation with the same characteristic, they do not have similar performance. So those 4 tasks are about the content. Probably I have to describe this figure a little bit. Here, here we show the Spearman correlation of different pairs of tasks. So each value here represents the Spearman correlation of a pair of tasks. And we have 10 tests here. So we have 10 times 10 values here. And the yellow represent very high correlation and blue represent small correlation. And we can find that for those tasks related to content, they do not have large correlation to each other. And the same phenomenon is found in speaker tasks and semantic tasks and so on. Then I found that if we sort the task in another order, we can find some pattern. Here I saw those tasks according to the number of parameters in the downstream model. And we found that here, those tasks, they have high correlation to each other. That is, if a model is performed well in one task, then it will also perform well in another task. So what is the common characteristic of those tasks? Actually, those tasks are quite different. We have keyword spotting here, we have emotion recognition here, we have intent classification here, we have phoneme recognition and speaker identification. Those tasks are focused on extract different kind of representation. They need different kind of information from the speech. But I found that their common is all the downstream model are linear model. So it looks like if the downstream model have the same network architecture, then the upstream model will have the same performance. But I do not really know the reason. I just showed you this phenomenon. And there's another thing I want to analyze is about the weights. So if some layer have larger weights, that means that this layer is probably more important for some specific task. And here is some result of the analysis. So here we show the weights of NPC and Web2Vec, Decora, and Huber. And the horizontal axis represent different layers. So here, for example, Huber from 0 to 12 means 0 represent the output of the CNN encoder of Huber, and 1 to 12 represent the 12 layers in the transformer. So if you are very familiar with the network architecture of this model, you know what I'm talking about. If you are not familiar with that, it's fine. Just consider here we have the weights of each layer for those for these 4 models. And you can find that if the task we are consider is phoneme recognition, then the higher layer, the layer close to the output, have larger weight. And if we consider ASR, the phenomenon is very similar. For the layer close to the output, they have larger weight. So we may draw the conclusion that the last few layers include more content information. Then how about other tasks? For example, let's consider speaker identification. So for speaker identification, we also show the weights of each layer for 4 different models. And you can find that now the behavior of those models are very different from their behavior in speech recognition. When the task we consider is speaker identification, then the middle few layer have larger weight. So it looks like the middle few layer contain more speaker information. We can observe very similar phenomenon for speaker verification. So it looks like for some of the self-supervised model, the last few layer contain the content information, and the middle few layer contain the speaker information. So in the round one, we can use all the layers, so those model can be universal in all the different self-supervised learning tasks, in all the different speech-related speech processing tasks. So here, I'm going to say my answer of this talk. So is this model specialist or universal? So based on the experimental result, it looks like they are universal. This is very surprising to me. However, I still have some questions. We already observed that those models contains some speaker information in the middle and some content information in the last few layers. However, don't forget that when we train the self-supervised model, the training procedure is task agnostic. The self-supervised model, when we do the pre-training, we do not know that we are going to working on ASR. We do not know that we are going to working on speaker verification. Then how can model know that it have to store some speaker information and store some content information, and they are stored in different layers? How can model achieve that during the training? I do not have the answer at this moment. This probably will be a very interesting topic for the further research. So welcome to join again. We have the leaderboard, and the leaderboard is already open. So you can find the leaderboard at superbenchmark.org. And welcome to submit the result of your self-supervised model. If you get any good result from your self-supervised model, welcome to submit to the leaderboard to see whether your model is universal or not, and to see whether your model can outperform the models here. And some people may think it may be tedious to working on so many different tasks. And we have a toolkit to help you. We have S3PRL, self-supervised speech pre-training and representation learning toolkit. You can find its link here. In this toolkit, you can easily access all different self-supervised models. So we have a unified interface for all different self-supervised models. So if you want to do some experiment to compare the performance of different self-supervised models, or you want to use different self-supervised model in your downstream task, S3PRL can help you. We have a unified interface for all the different models. And we also have script for all the downstream tasks. So if you want to working on those downstream tasks, you can leverage S3PRL, so you can easily work on a wide variety of downstream tasks. We have a video to introduce how to use this toolkit, but due to time limitation, I'm going to skip this page. So what's next for Superb? We are going to have Superb 2.0. The 10 tasks we just presented do not cover all the speech processing tasks. In the speech community, we have more interesting and important tasks, and we are going to cover more tasks in Superb 2.0. So we are working on out-of-domain ASR, we are working on speech translation, spoken question answering, speech enhancement, speaker separation, and voice conversion. And in round 1 and round 2, we put a very large constraint on the model. So probably some people are not happy about it. You want to know the full power of self-supervised learning, then you can do that. In the future, we will use other way to leverage self-supervised model. We will explore other way to leverage self-supervised model. For example, you can fine-tune them. You can add adapter to the self-supervised model. And we are not alone. Superb is not alone. There's another self-supervised benchmark called La Benchmark, but it's very different from Superb. It's focused on French. And it is also a paper at InterSpeech 2021. And if you have any good result about self-supervised learning, welcome to submit to AAAI 2022 workshop. We have a workshop, self-supervised learning for speech and audio processing. If you have any good result from self-supervised learning, or you submit your result to Superb and find out that your model is super good, then welcome to write a paper and submit to self-supervised learning for speech and audio processing workshop. The workshop submission deadline is November 12th. And after submit the paper to the workshop, you can extend it and submit to an IEEE JSTSP special issue. There's a special issue, self-supervised learning for speech and audio processing. So if you get some good result, you can write a journal paper and submit to this special issue. The deadline is December 31st. Is at the end of this year. And in the future, we plan to have a challenge for Superb, but it is not announced yet. Probably it will be announced in the next few months. If you want to get the information about the challenge, stay tuned to the Superb's webpage. I put the Superb's webpage here, or you can fill out the form below. So here I have a Google form. If you fill out the form, I can send you an email if the challenge is announced. And the QR code for the form is at here. So you can scan this QR code and to fill out the form. I would like to stop at here to answer some questions so the audience can have time to fill out the form here. So let's see whether the audience has some question. And I will keep this slide here so you can scan the screen. Okay, I think there are no question here. Is it?
Yeah, I mean, typically people are shy. So thanks again for the great talk. But yeah, oh, there is one.
Okay, so the question is Huber language specific, or it is or it is multilingual? Okay, Superb is trained by FAIR, and Superb is only trained on English, is trained on Libre Speech or Libre Lite. It has different versions, but all the versions are trained on English. So they are not trained on multilingual. But you can test whether they can apply on other languages. We do not have very concrete result at this moment. We are trying to use Huber on Chinese and also on code switching data set, but we are running the experiment. We haven't got the result yet, but for our preliminary experiment, it gets pretty good result. But this is something you can investigate in the future to see whether those self-supervised models are multilingual or not. Okay, so I have another question here. Does layer weights remain constant for various initialization in self-supervised pre-trained model? I think your question is, when we learn the layer weights, what is the initialization of the layer weights, right? They are uniform. So when we initialize the layer weights, they are uniform. How do we work with other languages? Can we train in lab for non-English language, or is it too much compute? I believe if you want to train those kind of self-supervised model yourself, especially if you want to train the model as large as web-to-vec large or Huber large, it is very hard to do that in a school lab. If you are in industry, you can do that, but in school lab, it's probably very difficult. But you can use them on non-English languages. Fine-tune do not take lots of computation. Pre-train take lots of computation, but in fine-tune, you only use very little data. So usually you can do fine-tune yourself. So you can see Huber is already pre-trained, it's off the shelf, and it's pre-trained on English, but you directly apply that on Mandarin, and you can see what would happen. There's a very good question. Can you speculate on why later layer are useful for extracting speaker and speech information? One hypothesis, but I'm not sure whether it is true or not. One hypothesis is if you want to extract content information, you need to know what is speaker first. So the model learned to identify speaker information in the middle layer. Then it subtracts the speaker information from the hidden layer, then obtain the content information in the last few layers. But this is just one hypothesis. I'm not sure whether this is true or not. And if this is true, probably you can observe the same phenomenon in supervised trained speech recognition. But if you analyze the speech recognition model trained in the supervised way, does it have some speaker information in the middle, then have lots of content information in the final layer? But I have never seen anyone report this kind of result. So to be honest, I do not know the answer. But this will be a very interesting topic. I encourage you to work on this to solve this mystery.
Can I ask a question?
Yes, please.
I think I got two questions. So first of all, about the Superb, about the Superb framework, have you So is everything including training, including evaluation, English only, or there is some other languages involved in the numbers you reported?
Oh, at this moment is English only. All the data set we use is open data set and they are all in English. So it's very easy for everyone to reproduce the result. And for Superb 2.0, I mentioned that we are working on out of distribution ASR. That means we are going to use the model trained on English on other languages, for example, Mandarin, to see what would happen.
Okay.
I hope this answers your question.
Yeah, of course. Yeah.
And you say you have a second one?
Yes, and the second question is that because this kind of Superb is is all about self-supervised learning. So, do you, because you got a challenge and you got a panel, so of course the lower the error is the better. But do are we- do we have any plan or do we have any idea on like what is the like some kind of good enough borderline for the model, or are we going to include any kind of supervised baseline to just as a kind of baseline to be there for people to
Yes.
for example, as a reference or as a or as something like a good enough thing, what I'm saying?
Yeah, this is a very, very good question. So first of all, at this moment, we do not add the supervised baseline because all the corpora we use, they are open corpus, they are open data. For example, for ASR, what we use is simply library speech. So it's very easy to find a baseline. But I think your suggestion is very good. So in the following challenge, probably we will show some result from supervised learning. So you can know the gap between supervised learning and self-supervised learning. So this is something we will do. And for the next for another question about how good so what is the threshold for a good model? I really do not have a good answer at this moment because there are many different factors in the whole framework. For example, we also have to consider the downstream model, right? So for some tasks, we use linear model, but if you use more sophisticated model, you will definitely get better performance. So, so there's a trade-off between the number of parameters in the downstream model and your performance. So I also have an idea, but I'm not sure how difficult to realize it is we should, for example, if we have the challenge in the future, probably we can say everyone can decide the downstream model yourself. So for all the tasks, you can design your own downstream model. We will compare not only the performance, but how much parameter you use in the downstream model. So if in the old 10 tasks, you only use very little number of parameter in all the tasks and you get good performance on most of the tasks, then probably this is a good model. But this is something still under discussion. So if you want to know more detail about the Superb challenge in the future, so please fill in the form. So I hope this answers your question a little bit.
Of course. Yeah, thanks.
Thank you.
And,
we have more question. We have more question below, but it's already 8:45. Should we stop at here? How you make the decision?
No, you keep answering. I guess we can because I steal some of your time. So.
Oh, okay, sure. So the question is, it's from Yadav. Did you try fine-tune the layer weights of the upstream model on all the combined tasks at once? We do. That will give us an idea of which layer is best for all the tasks combined. Okay. So what I think is a little bit from what you asked. So I get your question. We do not do exactly the same experiment as what you say, but we do one experiment is we do multitask learning. So we fine tune the upstream model and on all the 10 tasks, we fine tune the upstream model simultaneously for all the 10 tasks to see whether we can get better performance than just one model. And we found like multitask training is helpful. So we can get performance better than all the numbers I show in this slide if you do multitask learning.
Do you mind sharing the layer weight distribution, like which layer was more helpful for all the tasks combined?
Sorry. Oh, you saw which layer is more helpful for all the tasks? I get your question. This is a very good one, but we haven't really tried it. So I do not have the answer at this moment. So if you did get the answer from your experiment, let me know. Thank you.
Sure. Bye. Take care.
Thank you. Sunny asks, is it recommended to try transformer decoder for the downstream test? So you may find that in all the tests, we only use transformer encoder. We do not use transformer decoder. I think this is because actually most of the self-supervised learning we have at this moment, they only train the transformer encoder. They do not train a decoder. I do not really know what would happen if we also train a transformer decoder. I think APC probably can consider as a transformer decoder, but it only has the decoder, so we use it as the encoder. So I do not really have a clear idea what would happen if we use the transformer decoder. But of course, you can try by yourself. You can train audio version of GPT and see what will happen on Superb. Let me know if you get good result on the leaderboard. Kurimo asks more speculation. Would other speaker characteristic, gender, age, SN be best modeled by lower or higher layer than speaker ID? Very good question. I do not have the answer. Probably you can try by yourself. I think if we want to answer this question, we need downstream tests related to gender, age, and SN, right? If we have some downstream tests like gender classification, age classification, SN classification, probably we can answer this question. But we do not have this kind of test at this moment, so I cannot answer this question. But if you get the result, please let me know. Do I miss any question?
Nope, I think
oh,
you...
I think I...
Oh, you missed one?
Do I miss one?
I don't think so.
Okay. You think I already answered all the question?
Yeah. Maybe I'll steal
I think
one of the questions.
One from Ready.
Oh, okay, go ahead.
Okay. Does fine-tuning the self-supervised pre-trained model drift toward the downstream test, or will it still remain as universal feature extractor? This is a very good question. I'm sorry that most of your question I do not have the answer, but I think it's very easy to do the experiment. You can fine-tune the model yourself and to see the drift of each layer, and you can get the answer yourself and let me know if you get any result. Okay, I think I have answered all the questions.
Yeah.
Okay. So
thank you so much for the great talk.
So this is all of my talk. Thank you very much.
Yeah, and thank you so much for answering all the questions. Yeah, so if people have more questions, feel free to reach out, and I'm sure Hongyi will be happy to answer all of them.
Yes, I will be happy to answer the question.
All right, so the next one, we will have Chengyi and Yu. So hold on a sec, I'll make you guys co-host. Let's see. For some reason, I can't see Chengyi right now, but okay, fine.
Chengyi and I sit together, and we are in the same meeting room. So
got it.
Hello to.
Okay, got it. Okay, so Yao, do you want to introduce your colleagues?
Yeah. Hello, everyone. This is Yao from Microsoft. I'm gonna introduce next talk. The title of next talk is Building Streamable Transformer Model with Supervised and Semi-Supervised Learning. So will be presented by Wu and Chengyi Wang. Wu and Chengyi Wang are both from Microsoft Research Asia, Beijing, China. Chengyi currently is a third-year joint PhD student of Microsoft Research and Nankai University. Yu is a researcher at Natural Language Computing Group. Microsoft Research Asia. Their research interests are speech recognition and machine translation. They both have a very strong publication record in their research area. Let's welcome them. So you or Chengyi can take away.
Okay, can you see my screen now?
Yes, yes.
Okay, oh, great. Okay, hello everyone. My name is Wu, a researcher at Microsoft. And today, I'm very glad to be here to present our work building streamable transformer speech recognition model with supervised and semi-supervised learning method. And the topic of today's presentation is about how self-supervised learning helps the ASR model. And in today's talk, I will first introduce how we building transformer speech recognition model, and then Chengyi will introduce how we leverage huge unlabeled speech data to further boost the streamable transformer speech recognition model. And this work is a joint work with Jinyu, Yao, Xie, Kenichi, and Shu Jie. In the past 30 years, we have achieved great success in ASR field. About 30 years ago, we used GMM and HM method, and then in 2012, deep learning showed its power in speech recognition field. And in the past 10 years, we have many famous open source toolkits and some well-used products, and we even reach human parity on the switchboard benchmark. And now, about 3 years ago, Google released their on-device transducer model. The on-device model is an end-to-end model, and it's becoming more and more popular in these years. The on-device model is always available. It enjoys a low latency and a tiny footprint, so it can be deployed on the device. And because of the audio is never uploaded to the cloud, so the end-to-end model enjoys a privacy advantage. And the end-to-end model suffers from three main challenges. The first one is the latency, because the on-device scenario always requires a low latency speech recognition model, while the computation power of the device is not good enough compared to the machines deployed on the cloud. And the second one is the development cost. The end-to-end model is more data hungry than the hybrid model. So we have to obtain a lot of label data to develop an end-to-end model. And in this talk, we will focus on the two main challenges. And at the first, I will introduce how we develop a low latency transformer model. And then Chengyi will introduce how we reduce the development costs by leveraging the large scale unlabeled data for a speech recognition model. In the recent year, end-to-end ASR model have achieved great success. And the network challenge from the deep neural network to a recurrent neural network, and now to the transformer model. And for the transformer model, it also has some variants. For example, the Google proposed a very famous conformer variant. And according to an empirical study paper we published in the last year, for the offline case, the transformer always shows better latency, better accuracy than the LSTM model. And in addition to the offline speech recognition, the industry cares about more on the streaming solutions. And there are many ways to realize streaming end-to-end speech recognition. For example, there are streaming CTC, streaming transducer, MoCA, and trigger attention. And in our paper, we have done a lot of empirical study. And we found the transducer is the most robust and yield better accuracy on the large-scale data set. For more details, you can check out our papers. We show a lot of results by combining the different network blocks and different streaming methods. And in today's talk, I will introduce how our work at advancing the streaming transformer transducer family models. The transformer models, the transformer transducer models we use is shown in this slides. The left figure shows the transformer transducer structure, which consists of an encoder implemented by the transformer architecture, while the prediction network is implemented by an LSTM network. According to our experience, the LSTM prediction network can keep the same accuracy than compared to the transformer prediction, while the LSTM model for the predictor is more computation friendly. It requires low computation power device in development. However, if we want to, even if it is easy to train a standard transformer transducer model, however, there are several challenges when we apply the transformer transducer in the streaming scenario. The two main challenges are shown in this slide. The left figure shows the runtime cost and the memory are increased linearly with the increase of the history length. So if we deploy a naive transformer transducer model on the device, the transformer model will run slower and slower as the audio history becomes longer. And the second challenge is the look-ahead window grows linearly with the number of layers. For example, in the red figure, each layer only uses one future frame for computation, but the latency is accumulated as the layer become deeper. If there are 3 layers, then the latency accumulation becomes 3 future frames. And because we often use very deep transformer, for example, for some 1 billion parameters model, we use 48 transformer encoder layers. Then we will introduce extra 48 frame latency cost. And to deal with the problem, let's first recap the transformer computation. The transformer computation, the bottleneck of the transformer computation is the multi-head attention. The slides gives the computation of the attention module. First, we compute the attention weight, alpha, and then we apply softmax functions to weighted average the value vectors according to the attention weight, and the most straightforward ways to control the frame, whether the frame can see each other, is to apply a mask matrix. So we can use the M in the equation to denote the mask, and if M equals 1, and then the 2 frames can see each other, and if M is equals to 0, and then the 2 matrices cannot see each other. And in the following slides, I will introduce how we control the mask matrix to realize streaming transformer models. For the most straightforward scenario, if we want to build an offline transformer model, we could simply set the attention matrix to an O1 matrix, like what is shown in the red figure of the slides. However, if we just send in this step, the transformer model it cannot work in the streaming way. So we could address the attention mask slightly by setting the element below the diagonal to be 0. In this case, we could get a streaming transformer model. However, as we discussed before, in this case, in the last figure, as shown in the left figure, the memory and runtime cost will increase linearly. And in the ACAPS 2021, we propose a method which the core idea is attention mask. It's all you need to develop a real-time streaming transformer model. And in order to resolve the latency issue, we could further change the attention matrix as shown in this slide. We could only keep several nearest histories element to 1 and the other element to be 0. In this case, for each layer, we only need to use the previous three frames for the computation. And the computation only increase with the increase of the frames. In some scenario, in some scenario, a small amount of latency is allowed. So we can further adjust the attention mask accordingly, as shown in this figure. The real effect on the transformer is shown as left. In this case, for the F10, it can see the future 2 frames, and it can also see the history 6 frames. And for the future context, because of we set the trunk restrictions for F11, it can just see 1 future frame, and for the F12, it cannot see any future of frame. And by doing this, we can control the latency will not accumulate as the transformer encoders become deeper. And for the current transformer model, the look ahead window is 0 to 2 frames. And so its average latency is 1 frame. And in the decoding, we could also apply some tricks. The first one is we can catching the transformer encoder key value and the V vector value before which is computed before, and we just compute the query and key and value for the current frame at the time t, and we could also do some batching computation. And to evaluate our idea, we conduct experiment on Microsoft internal data site, which consists of 65K hours Microsoft internal audios. And the test site consists of 1.8 million words and cover multiple domains. The model size is 80 million parameters. And the parameters is comparable between RNT, transformer transducer, and conformer transducers. And the decoding is done on a very simple CPU. And the first one, we can see the comparison in the 0 look ahead scenario. We can see for the row 3 and row 4, we can see with our improvement, if we limit the history frames, we can slightly sacrifice the WER and further boost the real-time factor from 3.4 to 2.3. However, even if we optimize the transformer real-time factors a lot by restricting the history frames, the transformer model is still very slower than the RN transducer models. And compared to the transformer model and the conformer model, we can see the transformer is slightly faster, and they achieve a very similar WER on our internal text set. And to do the real-time decoding, we can use some batching to compute. And we accumulate several frames to form a batch to forward. And the batching technique speed up the decoding speed, while it may sacrifice some latency. We can see when the batch size equals to 5, the transformer and the conformer can be easily deployed on a single CPUs, and the RTF ratio is less than 1 significantly. And now let's turn to the second scenario. That scenario is we allow us a small look ahead, and currently we can see in this table the transformer model and the conformer model. When we can allow a small look ahead, it consistent better than the RNT model on both latency and WER. On the accuracy-wise evaluation, it achieved about 10 relative % gain, while it is even faster than the RNT models when the thread is 1 or 4. And if we compare the transducer model and the sequence-to-sequence model, we can see in the streaming scenario, the transformer model is more effective. And a possible solution is the transducer model is frame synchronized, so it can sync the decoding results with the continuous frames better than the sequence-to-sequence model. The sequence-to-sequence model have to output an end-of-sentence token to decide whether the decoding can be finished for the current chunk. And we also do some engineering effort to do the 8-bit quantization. We can see the iron model can enjoy better speed up by the quantization, while the transformer and conformer model can be only double the speed with the quantization. Besides the fixed trunk size models, we also propose an adaptive trunk size model in the last year interspeech paper. In these papers, the main idea is we can use an adaptive trunk where a stock network will decide the trunk size, and then the recognition network will be run when the trunk size is determined. And let me briefly show the evaluation results. The first one is the word boundary detection evaluation. The evaluation is not the WER evaluation. It is the accuracy of the word boundary detections. In the table 2, we can say when we choose different thresholds, the word boundary detection model will give different performance. If we choose a good threshold, the insertion and the substitution error of the word boundary is low. So it can give a very good precision in word boundary detection. And after the word boundary detections, we can run the speech recognition models to the current chunk. Here is an evaluation result on the LibreSpeech 960 hours training data set. And we can see in both of the base setting and the large setting, our accuracy is very competitive compared to the previous trigger attention model and transducer model. And here is our efforts on building high result ASR transformer model. However, there are about 700 language models, language in the world, and the data labeling is very expensive. So how to reduce the development cost is a core problem for the on-device transformer transducer model. And Chengyi will introduce how we reduce the development costs for the end-to-end model.
Okay, thank you. Hello, everyone. Next, I will introduce our recent work on semi-supervised pre-training for low-resource ASR task. The main challenge for low-resource ASR is that the large-scale labeled data is not available for the most of languages, and even for the rich resource language, this is also a serious problem for specific domains. For example, the background noise or distortion conditions can be vary greatly from the general domain. So to tackle this problem, one method is pre-training. In the supervised case, transfer learning can also be seen as supervised pre-training. It first trains a supervised model on multilingual paired data on the large scale supervised multilingual paired data, and then fine-tune the model on the low resource labeled data. This method have two advantages. First, the supervised data of the rich resource languages is easy to obtain. And second, this method works well for linguistic similar languages, for example, English and Spanish, but it cannot leverage the high resource unlabeled data. And for linguistic distant languages, the acoustic features for these languages may be far away. Another method is self-supervised pre-training or unsupervised pre-training. It can leverage the unlabeled data. The common training pipeline is it first train the model towards a well-designed unsupervised laws, and then it fine-tune the model on the supervised ASR laws on the low resource labeled data. The advantage of this method is the unlabeled data is easy to obtain, and we can leverage the labeled data or unlabeled data in the same domain or in the same language. But the shortcoming is that the self-supervised laws need to be well designed to learn the content information during the pre-training stage. In the last year in Europe, Facebook proposes a method for speech pre-training called Wave2Vec2. I will briefly introduce this method. The model uses the raw wave as input. It contains a convolution downsampling layer and a transformer-based context encoder as shown in this figure. Given a frame vector as input, the transformer model will mask some of segments and then feed the masked input to the transformer encoder. And then the model relies on a vector quantizer to generate some quantized representations. The input for the quantizer is unmasked. Given an input, the quantizer finds its nearest entry in the codebook. After we got the representation from the transformer and the quantizer, we can then compute the contrastive loss on the masked positions to optimize the network. Both the positive and negative samples are quantized representations, where the representation from the same position as the masked position is the positive example, and the negative examples are sampled from other positions in the same utterance. This model achieves super performance on public benchmark. The quantization module was qualitatively shown to learn a representation which can separate phonetic content from the speaker identity. They discovered the tokens learned in the unsupervised manner can be mapped to phones in a limited setting, but the method cannot leverage the multilingual supervised data. To improve the method, we propose a method called UniSpeech. It can learn a unified representation across different domains or different languages with both labeled and unlabeled data. This work is accepted by SAML 2021. In real case, it is less challenging to obtain rich resource labeled data, low resource unlabeled data, but the low resource labeled data is very scarce. So the transfer learning can leverage the rich resource labeled data to help low resource ASR, while unsupervised pre-training can leverage the unlabeled data to help low resource ASR. Our goal is to leverage all accessible data to learn the robust representations. So we propose the method called UniSpeech. Compared with Wave2Vec2, we first try to conduct the multitask learning. Assume that we have large-scale labeled high-resource data and unlabeled low-resource data. We add a supervised phonetic CTC loss during the pre-training stage. The CTC loss is applied on only the labeled data set, and the contrastive loss can be applied on both labeled and unlabeled data. This work is the first attempt to pre-train the speech encoder with both labeled and unlabeled data. However, we find this method gives little improvement. We think the reason is that the contrastive loss and supervised loss are optimized in different spaces, so it cannot guarantee that the learned representations by the unsupervised way are as useful as those learned by the supervised learning for ASR task. To address this problem, when calculating the CTC loss, we replace some part of the continuous representations with its quantized versions, and we compute the CTC loss on the mixed representations. Since the CTC targets Y is a phone sequence, so predicting Y with the quantized representations Q can get the quantizer to cluster phones and the quantized representations in the codebook. So in this way, the representations learned in supervised way and the unsupervised way are forced to project into the same space, and the two objective functions can optimize them, and it avoids the two functions optimize themselves individually. We first evaluate our methods on multilingual ASR benchmark. We use the Common Voice dataset. It contains speech data from over 60 languages. And in this work, we consider 8 languages for evaluation. The pre-training and fine-tuning data statistics are listed in these tables. And we either use only the speech or both speech and text according to different experimental settings. For fine-tuning, each language contains only 1 hour labeled data, and we fine-tune the model on each language separately. We mainly compare our method with 2 baselines. The first one is CTC transfer learning. We first pre-train a CTC model on high resource dataset and then fine-tune on low resource dataset. The second one is XLSR, which is the multilingual Web2 Web2. Our first experimental setting is a 1-to-1 setting, where we pre-train the model on only labeled English dataset and fine-tune on 8 low-resource languages. For XLSR, it cannot utilize the provided labels because it is an unsupervised method. So we can see that the CTC transfer learning baseline is slightly better than the XLSR method. That's because the transfer learning can leverage the label data to learn a better SR-specific representation, while our method can outperform the CTC transfer learning baseline as well as the XLSR baseline by 10% and 13% relatively. To utilize the unlabeled data, for each target low-resource languages, we add more unlabeled speech during the pre-training stage. And it should be noted that the transfer learning method cannot leverage this part of additional data. And so we can find that both XLSR and our method unit speech has a large gain compared with the previous setting. And also our method outperforms the 2 baselines by a large margin. We also evaluated our method on a multilingual pre-training setting. In this setting, the languages which has over 100 hours data are regarded as high-resource languages, and we then evaluate on the other 5 low-resource languages. For unit speech, it first pre-trained on the mixture of labeled high-resource data and large-scale unlabeled low-resource data, and fine-tune on the 1 hour labeled data set. So the conclusion is similar to the previous setting, and the results for all these 3 methods have a better performance than previous setting without the labeled multilingual data. We next perform an analysis of the discrete representations learned by the quantizer. And we want to investigate whether these representations can be mapped to the meaningful phonetic unit. And so we follow in previous work, we compute the discrete latence with the annotated fonts. We evaluated our method on the training data of TIMIT. It contains 5 hours of audio recordings with human annotated fonts. We computed the conditional probability based on the co-occurrence between fonts and the latents. This figure shows the alignment. We can see that our method can get a better alignment between the fonts and the latents, indicating we can obtain a good alignment. We also defined 2 metrics to quantitatively evaluate our method with the baselines. Compared with the contrastive learning, we find that unit speech can achieve more discrete more discrete code words in the code book, and it has a lower alignment entropy. This indicates unit speech is better at font clustering. We also conduct an experiment for domain transfer task. The source domain is the reading English, and the target domain is spoken English. We use library speech dataset as pre-training data and TED dataset as fine-tuning data. Unit speech also outperforms Wu to Wang 2 and CTC transfer baselines, shows the advantages of our methods on domain transfer task. Apart from unit speech, we also try to improve the recently Hubert model with the semi-supervised learning method. Hubert is also a self-supervised model proposed by Facebook. Its architecture are as same as Wu to Wang 2, except that it removes the quantizer, and during pre-training, it predicts labels. It predicts the pseudo-labels for masked positions. The labels are obtained by k-means clustering on the MFCC features in the first iteration, and for the second iteration, the pseudo-label is obtained from the pre-trained model after the first iteration. This method achieves comparable results with Wu to Wang 2. Though effective, it has higher computation costs because the iterative pre-training pipeline. To address this issue, we use semi-supervised Hubert. Instead of first pre-trained model on the pseudo-label got from the MLSLP feature, we can first train a CTC model on a small amount of labeled data instead of the, and then we can pre-train a new model on the pseudo-label got from the CTC model. And after the pre-training, we also fine-tuning the pre-trained model on the same labeled data to get the final results. Following the paper, we compare the target quality, the quality of the pseudo-label. The evaluation is performed on the validation sets of library speech. We first apply k-means with different representations learned by either the pre-trained model after the Hubert iteration 1 or Hubert iteration 2, or the representations from a supervised CTC model. And we compute 3 metrics: cluster purity, font purity, and phonetic normalized mutual information. And all these 3 metrics are computed based on the co-occurrence of the labels and the fonts. The results show that the features learned by a CTC model are much better than the features learned by the unsupervised models in both iteration 1 and iteration 2. We compare our method with Hubert on library speech benchmark. We first pre-train it on, for the Hubert baseline, we first pre-train on the 960 hours of unlabeled data, and then fine-tuning on the 100 hours labeled data. For semi-supervised Hubert, we first train the CTC model on the same 100 hours labeled data. And after that, we pre-train a new model based on the CTC features, and then we fine-tune it on the 100 hours data again. Compared with Hubert, our method don't use any additional data because our the pre-training data for the CTC model and the fine-tuning data are the same 100 hours data. And our method can outperform the Hubert after iteration 2 over 10% relatively, and it only requires 66% of the training GPU hours. The self-supervised learning method has achieved great success in low result scenario, but the common wisdom is that the self-supervised learning helps where only a small amount of labeled data is available. To our knowledge, at most a few thousand hours of labeled data was used in the study of self-supervised learning. In contrast, the industry usually uses tens of thousands of labeled data to build a high accuracy ASR system for rich resource languages. So to further evaluate the effectiveness of semi-supervised learning when large-scale labeled data is available, we extend our unit speech on Microsoft product data. We propose unit speech at scale. We make the following difference to be comparable with our product baseline. First, we use F-bank features instead of raw wave input, and we replace the quantizer with a linear layer. And also we replace the CTC loss with the transducer loss for better SR performance. Finally, the model is trained in a streaming mode. We pre-train the model with 220,000 hours of unsupervised data and then fine-tune it on 64,000 hours of labeled data. To prepare the unlabeled data, we collect diverse audios with different background audios, and it has accent speaker speech as well as speech sampled at 8,000 hertz. And for the labeled data, for the labeled 60K hours data, it has cleaner background, and all the audio are sampled at 16K hertz, which we will refer the domain for the 60K hours labeled data as in-domain data. We have several test sets. The task A and task B have the same domain as our supervised training data set, while task C is a conversation task, so it has a different domain with the labeled data, and it is sampled at different frequency. This task is an out-of-domain test set. Task D is an accent English task, and there are also other test sets from 4 English-speaking countries. In our experiments, we find the contrastive-only pre-training decreases the performance slightly compared with the supervised training. For in-domain tasks, our unit speech has similar results as the baseline. This is expected because the domains are highly related for the labeled data. And for the out-of-domain tasks, unit speech significantly outperforms the baselines. And on accent evaluation, the conclusion is consistent with out-of-domain evaluation, but the gain on the accent citing is smaller. Let me conclude this talk. First, we introduce our technology to build the transformer-based streaming ASR model. By designing the attention mask, we can control the receptive field and balance the performance and the computational cost. And we also propose the Scott network to make a trade-off between the latency and accuracy. Next, we introduce our 2 work on semi-supervised learning, and our method can achieve competitive results on both public baselines and also our product models. In the future, we will continue to explore how to learn universe representations, not only for multilingual ASR tasks, but also for more speech-related tasks, for example, speaker identification or spoken language understanding task. And apart from unlabeled speech, we can also obtain large-scale unlabeled text. So how to leverage the text data and jointly learn from both audio and text modality is also our interest. Finally, we will scale up the model size to explore the potential of the pre-trained model. That's the end of my presentation, and thank you. If there are any questions.
Yeah, thank you, Chengyi and Wu. Now it's time to take questions.
Maybe I'll just kickstart one. So when you train your uni speech model, it seems like the ASR multitask, the other task for ASR helps quite a bit. What do you think ASR is so special about it, or maybe some other task would do equally well?
Actually, currently we only evaluate on ASR test. So we add the CTC loss in our pre-training stage. And our goal is to learn an ASR specific representation. And I think if your downstream task is other task, for example, speaker related task, maybe you'll need to add other pre-training task.
Yeah, I think that is a good question. But I think the answer depends on how large is your downstream task label data. I think ASR is a special case because we always label a lot of data for ASR supervised model training. So I think for ASR model, the supervised data is quite large. But for some other downstream task, for example, for some derivation task, the label data may not as large as the ASR model. So I think the answer might different for some other downstream tasks, especially for the task that have very limited label data.
Thank you. I remember when Professor Li gave the talk. So one of the audience raised the question like how about the pre-training with multilingual data? So here, Chengyi and Wu's work, they want to pre-train a model to leverage both label data and unlabeled data. So it's I think they try to solve the problem that for the scenario that for the multilingual, at least you have a few of the label data for all the language. And so combine this all the label, the small size data, we can further improve the performance. Okay, so.
Oh, there are questions coming in now.
The necessity of VQ, according to our experiment on deliberate speech, the VQ might give about 10% gain on the WER. However, if we introduce VQ on a large-scale data set, we have to tune the diversity loss, the IR loss, and the constructive loss. So the VQ might also introduce more efforts on hyperparameter tuning. And so I think if we can get a good hyperparameter, the VQ can bring some gains on ASR. The question is, how many hours of pre-trained and label data is required to build a good non-English ASR? I think for pre-trained data, the pre-trained data, we can use some unlabeled data. I think it at least over 10,000, and for the label data side, I think it depends on how you will use the ASR data. If you want to build a general ASR model, I think the data size should also be larger than 10,000. But if your use scenario is very restriction to a very specific environment, the data you use can be less. For example, maybe 1,000 or 2,000 are enough. And the questions, in some settings you use VQ and in the others you didn't. Yes. Yes, in the public benchmark experiment, we use the VQ component, but for our internal large scale setting, because of we cannot find a good hyperparameter according to tuning, so we just remove the VQ component.
So I think we almost use up all the time. So how maybe we can move to the next session?
Yeah, maybe let's just take a break, and then we can come back at, let's see, how do I refer to this? Let's come back at 1:45 UTC plus 0. Yeah, so let's take a break. Jan, I'm not sure if you can hear me, but I've made you a co-host, and if you want to test out, you know,
sure. Let me see how it works. It's probably too dark right now. Let's see if this. Let's try to make the camera work. No. So let's leave it like that. And let's try to share screen. Okay. Okay, you should be able to see my screen right now, and I should be able to scroll to the beginning.
Yep, I can see it all right.
Okay, perfect. So we roughly start in 5 minutes, right?
Yeah.
Cool.
Wrocław. Wrocław. Wrocław.
All right, I guess we can start. So we're happy to have Jan Chorowski, and he is right now an associate professor at University of Wrocław. I hope I pronounced it correctly.
Yes.
That's my best approximation of that word. Yeah, but Jan is well known for various work in the field. So I'm probably, many of you have seen his pioneering work in end-to-end ASR with sequence-to-sequence models and lots of different models for zero speech challenge and so on. And in fact, today he's going to talk about unsupervised learning for unit discovery. And so, yes, Jan, take it away.
Okay, thank you for the introduction. So because this talk will touch upon a few things I have been working on, there is a little bit of an outline so that everyone knows where we are at. So I'll try to motivate why to do unsupervised learning and what do we hope to achieve right now, and then show some results on essentially autoencoders, and then show two results on how to enforce a latent structure. So basically talk about which properties of the latent structure we would want to enforce for unit discovery, and then how we can achieve this both for autoencoders and for the more recent contrastive coding approaches. And then finally highlight how we want to move forward with it also in the context of the zero speech challenges. So deep learning, the most awesome thing about it for me is that you can feed into a model essentially the raw data, so say raw pixels, raw waveforms, the rawer the better, right? And then on the other hand, ask the model to produce some high-level concepts. And that's basically this. So you put in the input image or the input data, you provide the labels, and then you tweak the neural net until the output of the network on your input starts to resemble the output, the desired output. And the network is deep, namely the computation goes in several stages, and it tends to discover the important features of the data throughout these stages. So for instance, for visual models, the very well-known result by Matthew Ziller is that the early layers learn to be edge detectors or corner detectors, and then the later layers learn to detect certain concepts such as a dog's face. And this, of course, this was the premise of deep learning since its very inception. So 35 years ago, Jeff Hinton was describing a deep neural net as something which has internal hidden units, which are not used representation, but quantized, so low information content, and which is trainable, as Aaron van der Noord and co-authors have shown, using some tricks on gradient propagation. So this is not the exact gradient, but it's good enough to train this model. And then having those discrete features, we can use some powerful generative models such as WaveNets or pixel CNNs to reconstruct. So they basically take some rudimentary conditioning and then regenerate the sequence a column by a column. And they work decently without any conditioning. That's the picture on the left. So this is what you can get when you try to synthesize handwriting without any conditioning at all. Sometimes it's okay as in the middle line. Sometimes it loses the baseline. When you condition on something like the characters, so very little information, it tends to regenerate proper lines and maybe even have some resemblance. So for instance, these are two regenerations of the image on the left. And for instance, the D character here could be seen in both lines. So they learn to keep some properties of this. On the other hand, this reconstruction algorithm takes care of all the little details like continuing lines and so on. So this looks like handwriting, although a pretty bad one. And I have evaluated how much you can get using this model. So basically, we did this for audio. We either took raw waveforms or some speech features, such as ML filter banks or MFCCs. Then we ran it through some convolutional encodings. We tested 3 different kinds of bottlenecks. So dimensionality reduction, the VAE bottleneck where you inject noise, and then the VQ bottleneck where you quantize rather than injecting noise. So the dimensionality reduction only indirectly loses information because it projects stuff into a lower dimension. The VAE bottleneck, so noise injection and sampling from a Gaussian, and the VQ VAE direct rounding, they both essentially lose information, and both can be, and the amount of information lost or preserved can be expressed for both of them in bits. And then we combine this latent encoding with speaker information and run the WaveNet to reconstruct the input waveform, and this provided training signal. And we also briefly explored with reconstructing the filter banks, but this never led to some good results. And what we were interested in is what happens to the information which goes through the system. So are we able to really, say, have speaker-independent features? And to test it, we placed several of those probing points at different locations in the network. So basically, after the encoder, after a dimensionality reduction, after the bottleneck, and then after a few convolutions which would mix neighboring latent signals and feed this into the WaveNet. So we had those 4 points, and we were interested in preserving as much as possible of the phonetic information, and then discarding as much as possible of the speaker, which was provided using the sides channel. So we hope that if the speaker is given in an explicit way here, it will not be remembered the latent representation where the model is really forced to optimize it under a capacity constraint. And the major result is summarized on this picture. So basically, we are plotting here the phoneme prediction accuracy, so the higher the better, versus gender prediction accuracy. Here for us, the lower the better, because ultimately we want the representation to be speaker insensitive, so also gender insensitive. You cannot tell whether the utterance was uttered by a male or female, but you can tell what are the phonemes in it. And ideally, we would want to be in this lower left upper hand corner, where we do well on phoneme recognition accuracy, and we discard this gender information. If you move on the diagonal, it really means that the model discards both informations at the same rate, which means that, I don't know, it's discarding information or adding noise, but it's not doing something sensible. And in fact, the VQ bottlenecks, they tended to be in this upper hand corner, where the phonetic information is mostly preserved, so there is a slight loss of information, but it's also very selective. So we discard nearly all of the speaker information. Like predicting gender is pretty easy on audio. The F0 is just very, very visible on spectrograms. So this shows us that we can use those deep models to produce good representations on which we can try this clustering and segmentation. And in numbers, we evaluated this on data from Zero Speech 2017, and this model yielded nearly state-of-the-art performance on most of the languages, with the exception of Mandarin. And perhaps it's because, according to the Zero Speech 2017 rules, Mandarin had very little unsupervised data, like 2.4 hours of unsupervised pre-trained data, which is really, really small. But also maybe because we tried to discard the gender information. In fact, we discard the tones, which are meaningful in Mandarin. But this model was a good starting point for trying to do this joint clusterization and segmentation, to which about which I want to talk right now. So now that we have a model which is able to provide this high-level information, discard what we don't want, I would want to show how we can try to enforce some properties about the structure of the latent vectors. In other words, how do we learn to segment, or how do we enhance the segmentability of the representation? So let's say that we have our audio signal. And the easiest we could do is to extract the latent vectors uniformly in time. So say we take them every 10 milliseconds or every 50 milliseconds, or roughly at the frequency of the phonemes. But of course, this is uniform, and the duration of data, which really means that we can take like the average phoneme duration or the average character density to specify it. And then this makes it a very easy hyperparameter to set. And we can also solve this joint quantization with a pretty fast greedy algorithm. So this can be put inside of the training loop of our system. And this worked. What do you do during inference? So what does it really mean if we take a large chunk of data and we enforce our representation to be piecewise constant with a predefined number of segments across a whole chunk of data? How do you apply this to, say, segment a single utterance? So you go from this constrained program to optimization problem to an unconstrained but penalized one. And now you see that essentially this is the same as using a Lagrange multiplier lambda, which is essentially a cost of changing the symbol. And this has a very nice interpretation. So from optimization theory, we know how to set lambda based on the solution to this constraint program. So the lambda is essentially the slope of this cost as k changes near the optimal k. So this is easy to set. And what's nice is that this penalized program corresponds to the simplest dynamics that we could have, which is like an HMM. Essentially, we either we either change the symbol and follow one arrow, or have a self loop with a cost of 1 minus lambda. So this allowed us to essentially put a very simple Markovian prior on top of the latents, even though we did it in a very indirect way. And the imposition of this piecewise constant bottleneck improved our results on nearly all the tasks on the character recognition domain. So this improved downstream character recognition. This improved the ability to predict the characters at the bottleneck, and this improved some clustering scores just by putting this one prior on the later representation. However, people have discovered better ways of learning representations, and in particular, right now, the dominant approach seems to be those contrastive coding approaches. And so, what I want to show you right now is how you can try to impose those the same kind of a penalty. So, how to promote piecewise stability, piecewise constantness, but for contrastive coding models. And this is an approach we called aligned contrastive predictive coding. So contrastive coding approaches aim to learn the representation without the decoder. So there is, I guess they will introduce at the same time, there is the contrastive coding from Van den Noord, and then there is also a wave to back from Facebook that Michael Auli will talk more during this workshop. And in both of these approaches, I'll use the CPC as an example. The model takes frames, so takes raw speech in frames, then runs them through an encoder, then creates a sequence of latent representations, those blue boxes, and then tries to model the dynamics of those blue boxes, so of the latent representation. So it takes the encodings up to time t, perhaps applies to them like a recurrent neural net or something like this to aggregate the information up to time into a context vector CT, and then predicts the frame ZT plus 1, ZT plus 2, and so on, and trains the model to essentially model a non-trivial dynamics in the latent vectors. Now, the main trick to get it to work is that we are not predicting the next frame. If we were to predict the next frame, the model could cheat. It could say, choose to have a 0 latent representation, very easy to predict. And instead, we are using this contrastive loss in which we ask the model to classify, say, the frame ZT plus 1 from a randomly sampled frame from the utterance. So how to best explain this? So in this model, we don't have the decoder, but we assume that there is a latent signal underlying our representation, and that this latent signal is properly compressible. We can essentially learn its latent dynamics, and anything which has those latent dynamics is the underlying truth in our representation. This matches well the speech, where we assume that there are phonemes which you could model with a phonetic language model or handwriting with characters. But the system is really frame synchronous or time synchronous. So we make one prediction for every time step, and there is no notion of a unit. And also, because the system is inherently taught to say differentiate between the prediction at t+1 and t+2, it's not incentivized to model a piecewise, to learn a piecewise constant representation. It's incentivized to use anything that separates two frames, even two neighboring ones, to encode it so that it can discriminate between them. And our idea to make it more piecewise friendly was to essentially predict fewer frames, make fewer predictions than the number of upcoming frames that we'll be matching it to. So I'll try to explain this using the cartoon. Let's say that we wish to predict the 6 upcoming frames. If we were doing the contrastive coding, the vanilla one, we would have to make 4 or 6 predictions for the next 6 frames. Instead, we are only doing 3 predictions. Then, within our training loop, we align those 3 predictions to the 6 upcoming frames. And then we essentially train this as usual using the contrastive loss. So in the picture, you have the 3 predictions here. You have the next 6 frames here. The color intensity in this table is essentially the similarity of the prediction and the frame computed using a contrastive loss with negative samples and so on. And we run a dynamic time warping to find essentially the best assignment. And then we train the model to reinforce this best assignment. In other words, we change the cost function a little bit. We are not predicting what will happen 5 frames from now. We are predicting what will happen and approximately when. We let dynamic time warping to align our what predictions to the exact timings. This also enforces this piecewise constant representation, because if you have several frames aligned to the same prediction, like say you have those 3 frames, zt+1, zt+2, and zt+3, aligned to CT, right? They will be trained to essentially match the same prototype. So they will be trained to be similar to this prediction, and this means that they will be trained to be self-similar. Now the ZT+4 can be totally different because it got aligned to the next prediction. And of course, the ZT+5 and ZT+6, they were aligned to the 3rd prediction, and they can of course also learn to be different from both the first 3 frames and the 4th frame. So this mechanism wants frames aligned to the same prediction to be similar, but really allows sharp transitions when the predictions change. And what does it change qualitatively? On the 2 plots below, we are showing the frame-wise similarity for CPC and ACPC. So basically, every row and column here is the similarity between 2 frames. On the diagonal, we have the similarity between the frames themselves, so say the length of the vectors. And then what we would really want to see is those blocks of self-similar frames, like here, which we could call a unit, right? Because this is a block where all of the frames are similar to all the other frames. And in fact, we see that for ACPC, for this aligned variant, such blocks start to emerge, and they even coincide with those thin white lines, which are the ground truth phoneme boundaries. So basically, not all the boundaries are there, but for instance, we do have a phoneme here, we do have a phoneme here, we do have one phoneme here. On the other hand, for the vanilla CPC, we see faint impressions of these phonetic boxes overlaid with this highly visible pattern, which of diagonal lines separated by a few frames. And I believe that this is an artifact of essentially the ConvNet learning to how to encode the relative position. I don't know, maybe it's due to some mismatch of the sampling frequency of the microphone and then the strides or something like that. But basically, because it was asked to find something which discriminates between neighboring frames, in fact, it learned how to encode the relative position, and this really hides the more interesting signal of which groups of frames are important and where are the phonemes. And this was confirmed by us by analyzing the similarity between random frames. So those two plots on the right. If you take two random frames and compute their similarity, the two systems behave similarly. However, ACPC has this bump here, which means that some frames are fairly similar, and this we found that this is really the difference in the similarity of consecutive frames. So for ACPC, most of the time consecutive frames are very similar, as opposed to CPC, which essentially doesn't try to have consecutive frames similar. And of course, we want consecutive frames to be similar most of the time, because that's what should happen in a piecewise constant representation. And this also leads to better clusterability of the representation. So we looked at the mean square distance from a sample to a centroid. So basically the k-means error, and this is lower in terms of for ACPC than for CPC. And we also looked at the mutual information between a clustering and the ground truth phoneme labeling. And again, this ACPC has a higher mutual information, so it's clusters better and also corresponds better to the phonetic segmentation. And this, in fact, translated to better scores on the zero speech baseline. So the ACPC beat the CPC baseline on the ABX task, which is a phoneme discrimination. And it also improved by nearly 2 percentage points the ability to linearly classify phonemes based on the latent representation, either the encoded vector ZT. So there is a jump from 51.5 to 52.2, and on the context, where there is a jump of 67.8 to 69.7. So nearly 2 percentage points of improvement, just because we have applied this piecewise constant prior on the latent representation. So finally, how this translated and how this plays in the zero speech challenge. So this year's zero speech was special because it had 2 tiers, a low budget tier and a high budget tier. And unfortunately, we had the resources to only compete in the low budget. So we didn't really try to do this ACPC on the full zero speech data, because we didn't have the GPU for it. So I can't tell you how much this would improve this the results, but we did try to impose a few other cleanup techniques to the representations. But just to tell you what was in the zero speech, this year it consisted of 4 tasks. So there was a representation learning task measured by the ABX error scores, which basically aimed to uncover correct encoding, latent encodings of the data. Then there were 2 tasks on word discovery. One lexical, whether in which we were supposed to tell whether a word is out of vocabulary or in vocabulary, and then a semantic one where short snippets of audio should be put into a vector space in a way that word2vec does it. And then finally, there was a syntactic task in which one had to separate between grammatical and ungrammatical sentences. I will only show you the solutions to the first 3 because we didn't really have a strong entry into the fourth category. Now the organizer of zero speech have provided a baseline solution in which the audio was put through a CPC model, the vectors were clustered using k-means, and then in their LSTM or a BERT encoder was trained to solve these tasks on the k-means representation. So there is this discretization or unit discovery phase. And for the results, I guess that because of this 2 tiers, essentially all the contestants competed in the low budget tier. So no one really redid the acoustic model. So everyone used the same CPC model that was provided by the organizers. And we managed to improve very slightly the results using some post-training cleanup of the representation. Then we did fairly well on the lexical task, and also had some success on the semantic tasks. So this discovering word meaning, which I believe is the most promising one and which we are working right now. So what exactly did we do? For the phonetic task, we tried to remove speaker identity using a very simple trick which improved the results of the pre-trained model by just a tiny bit. So we want to show it. And so what we did is we took the latent vectors, we trained the speaker classifier on top of them, and then we projected everything onto the null space of the speaker classifier, hoping that if some directions are important to classify speakers, if we project onto the null space, so onto the directions perpendicular to it, we will remove speaker information. In fact, this did improve by a tiny bit the ABX score, so essentially the truthfulness or closeness to phonetic representation of the CPC vectors. So it's a very simple method that can be applied to the outcome of any model to remove unwanted information. And then we also discovered that it helps a little bit if you push the representations towards a clustering. And we also tried this during training, and enforcing clustering during training in general helps. So there is something to the VQ bottlenecks in general to enforcing quantization during training. Then for the lexical task, we decided to try the simplest thing, which is trying to find each query word in the corpus. So what we did is we took the k-means representation and they ran a dynamic time warping across the full Ribley speech corpus. And then whenever there was a match, with some scaling of the score, we reported that the word is in vocabulary, and whenever we didn't find something, we reported this as out of vocabulary. And this worked with some tweaks to the distance matrix taken as the distances between the k-means. And the take-home message for me from this task is that we do have very good representation learners right now, and they are good to a point that you can cluster the results and apply discrete algorithms, and they are extremely fast. So we are somewhere near the point where this representation is usable using fast algorithms which don't work in this vectorial space, they work in a discrete space. And we use something very similar for the semi task, where the task was to discover word vectors, word vector meanings. So we tried to do an analog of word to vec. And what we did is we took this k-means clusterization, then we heuristically cleaned errors and removed repetitions to get, say, a sequence of pseudophones, so to align the representation with phonemes. Then we applied the sentence piece method to find frequently co-occurring patterns of phonemes, which we could call pseudo words. And then we applied the word to vec method to find the meanings of those discovered words. So essentially, those tasks would be learn a good representation, then do a clustering of the representation to get the units. This clustering should involve some sort of segmentation, really. And then if you have proper units, you can redo this clustering plus segmentation, but on a larger time scale to go from single units, so characters or phonemes, into words. And then once you have words, you can use tools to discover the meaning of words. And this worked by a little bit, to be honest. The scores here are percentages of a correlation between human relatedness between two words for humans and what the algorithm said. So a 10 here really means 0.1 correlation, which is nearly random. But our say enhanced baselines, which try to apply word to vec to sentence piece tokenized Libri speech transcription, says that if we had proper phonetic representation, this should be about 30% or 0.3, not 10. So we believe that the bottleneck right now is in this higher level unit discovery, and this is what we are attacking right now. And I guess that's a very good moment to do so, because we get representations which are good enough to essentially employ discrete algorithms. So edit distance, the sentence piece thing, which tries to find co-occurring, frequently occurring sequences of units of characters to do word type discovery across huge data sets. So to summarize, I have shown, and I guess that the time is right to, we do have very good algorithms right now to discover latent variables for sequential data. We have reliable tools to control what's in the latent representations. So we can remove the information either during training by putting those side channels for the information we want to discard, or by post filtering, even using something as simple as essentially going into the null space of a predictor of the information we want to discard. And then we can also try to aim, try to make this representation piecewise constant, so enhance its clusterability, and then work on clusters using algorithms made to work on character sequences, so very finely tuned algorithms to be able to cross-correlate and find repetitions in large corpuses. And this should allow us to do large-scale word discovery or large-scale unit discovery in large corpuses. But this is still the beginning. We need to find something better to really learn the meaning of words from raw waveforms. So thank you for listening, and I do hope you have questions.
Thanks, Jan, for the great talk. So if people have questions, feel free to put them in the chat, or if you want, you can unmute yourself.
I have a quick question. You mentioned that you did speaker factorization on top of CPC. Does that require a speaker label, right?
Yes.
Okay. So that's not unsupervised then, right? Because you require a speaker label.
No, it's not fully unsupervised. It requires speaker label, but it doesn't require, say, the phoneme or. So for zero speech, the assumption was that we do have the speaker labels. You could possibly, you could do it across utterance or something like this, assuming that there is only one speaker per utterance, or apply some more classical diarization, but then the errors would probably compound. So this is some supervision, but not on the core task.
Okay, thanks.
There are a few in the chat. Jan,
Yes,
yeah.
I do see. So there is a question about how does piecewise constant constraint conceptually match with co-articulation, context-dependent phonemes? So I guess that for context-dependent, it's assuming that you do hear several sounds, right? So do you modulate whatever the middle phone sounds like, but you still hear it separately from the two lines and closing it. This should help. But there is no guarantee that you will essentially find one segment per phoneme. And in fact, what we have seen is that if you have two phonemes which frequently co-occur together, so it's not even that one of them modulates each other. So it's not a context-dependent realization of the phone. It's just that a pair of phones is a very frequent unit. And then the system would essentially learn to encode them using the same vectors. So if you force this piecewise constant representation, it may want to model some pairs of phones or pairs of characters as one unit. And I guess it will be really hard to prevent the system without any background knowledge. But I don't know if this is really important to get the phonemes exactly 100% right. If your goal is to, say, detect words and you are consistent in gluing pairs of phones together, maybe it's okay. At least that's what we hope. I don't know if I answered this question. If not, please put more into the chat. Then the next question is, what has your experience been with out-of-domain variations, exempli Gracia? Say you account for speaker variability using the null space. How do representations work, for example, with a different accent? Well, that's a tough one. I don't have any hands-on experience with how the model would approach it, but I believe that unless you really have data which would give you some accent labels or things like that, the model would stay confused. So that's a tool to remove some trait, but you have to have the labels for that trait. but I can't tell you how much or how little you would gain out of say trying to post hoc remove this accent information. And then the next question, how well does this model work on languages which share common fonts or basic units? Will the latent representation remain similar for same sound units of similar languages? So this is something that we have to try. I do believe that something similar, something reasonable would happen, but I only have indirect results for it. So at some point we were trying to do some NLP systems, so a parser for joint languages like Polish, Russian, Czech, and so on. And especially for Polish and Russian, it was funny because we fed it the Latin alphabet or the Cyrillic alphabet. And in fact, the early embedding layers for matching Cyrillic and Latin alphabet letters, they started to be parallel. So I would assume that if you mix different languages, then the similarly sounding phonemes would cluster together. But this is very indirect experience. So the last one is, do you think it's possible to have unsupervised acoustic word representations without the help of other modalities, exempli Gracia images or words? So possibly yes, but I guess that the words can be a very efficient way well, the visuals can be a very efficient way to co-supervise your model. I mean, right now we do aim to have representations that you can cluster, and this clustering has high mutual information with say the phonetic segmentation, but it's not supervised on something. And then if you just take a phonetic transcript of your corpus and you apply something which finds frequent co-occurrences of phones, such as say sentence piece, you do get many of the words. So to some extent, this is doable without images or other modalities. But then I guess these other modalities would help. So you would see that impact as lowering the size of the corpus. And then finally, I guess that's a little point of critique. So to make a more careful use of the, all right, yes. So I accept the critique and will try to use it better. So to separate between the phonemes, phones, and whatever we assume we have discovered as phonemes, because I believe that this is the this is what this piece of critique is about. So thanks for the link.
All right. If there are no more questions, let's thank Jan again. And yeah, if you have more questions, feel free to send me or Jan questions offline. I'm pretty sure Jan will be happy to answer any of them.
Sure, I will be here also. So.
Okay, thank you so much.
Thank you.
So for the next talk, Preeti, do you want to introduce the speaker?
Sure. Odette, do you want to try? Hi. Do you want to try sharing your screen?
Yeah, that might take a while as usual. Screen 2. Let's see whether that works. And then, okay, because now I'm losing. Oh, where are you? There you are. Okay.
Yes, we are live.
Yes. Okay, cool. That worked.
Great. So I think we're doing good on time. Happy to see everyone here. So I'm very happy to introduce our next speaker, Odette Sharenborg. She's an associate professor at Delft University of Technology. And this is paraphrasing from her webpage. She has an interest in anything and everything related to speech, human and automatic speech processing, non-nativeness, under-resourced languages, emotion, background noise, and any permutations and combinations of these topics. And today she's going to be talking to us about unsupervised subword modeling using cross-lingual knowledge transfer. So over to you, Odette.
Well, thank you very much. And thank you also very much for inviting me to present this work here today. I'm slightly nervous about presenting this work because it's actually not really mine, in the sense that it's work done by a postdoc in our group, Xu Feng. So I tried to get this presentation together the way I view his work, but I'm very happy with the work that he has done. So I'm very happy to be presenting it here today. But it also means that if you have any questions about the details, please either check the papers or contact me or Suyuan, and then we can answer questions. So these questions will be a bit more difficult because this is more of a global talk about the work that he has been doing in the past 2 years while he's been in our group. So this is about unsupervised subword modeling using cross-lingual phone-aware modeling. Let's see how this works. I'll do it this way. So the ultimate goal that I'm interested in ever trying to accomplish, which will be probably way beyond my lifespan, is automatic speech recognition, or ASR, for all the world's languages and all types of speech. But as you are aware, I assume there are many languages in the world. Depending on how you count, you have approximately 7,000 different languages. But if you look at the number of languages for which we have automatic speech recognition systems, this is approximately 2%, which means that for 98% of the world languages, there simply is no automatic speech recognition or actually speech technology in more general available. Now, why is it so difficult to build automatic speech recognition for all the world's languages, or rephrasing that? So why don't we have ASR for all the world's languages? And that is because the way ASR systems typically are trained. We have, when we train our ASR systems, we need a lot of speech data with the transcriptions in order to build our acoustic models. And we need a lot of text data in order to build our language models. But for many of the languages, we actually only have speech available, and sometimes with a few transcriptions or with a bit of text. So we just simply do not have enough data available for many languages in the world, which means that it's really hard to build these ASR systems. On top of that, for many languages, we actually lack the linguistic knowledge, or it is incomplete. So to sum up, basically this means that conventional supervised acoustic modeling techniques, where we have transcriptions and the speech data in order to train our acoustic models, can simply not be applied directly. And that means that in our current situation is that we have high performance ASR systems only available for a very small number of the major languages, for instance, English and Mandarin. Now, to facilitate ASR technology for low research languages, so languages for which we do not have a lot of data, be it speech data or with or without transcriptions, one way of dealing with that is by looking at unsupervised acoustic modeling. So finding a way of building our acoustic models without the need for supervised training. And the aim for unsupervised acoustic modeling is to find and model a set of basic speech units that represent all the sounds in the language of interest. So this is our low resource or our target language. So can we find the basic speech units that represent the sounds of that particular language in an unsupervised way? Now, the critical assumption underlying UAM is that we only have the raw speech data available. So we do not have the transcriptions, we do not have the phoneme inventory, and we do not know the size of the phoneme inventory. All that is unknown. And this is also referred to as the zero resource assumption. Now, there are two main research strands for UAM. The first one is acoustic unit or acoustic model discovery, AUD, where the aim is to discover a finite set of phoneme-like speech units. So this is the ultimate goal of UAM. And the second strand is unsupervised subword modeling, or USM. And there we want to learn the acoustic feature representations that can distinguish subwords, typically phoneme units, of the target language, and is robust to linguistically irrelevant factors such as speaker characteristics. So basically, the second research strand is learning an intermediate representation towards the ultimate goal of UAM. So There are two main research strands, but only one of them actually directly focuses on the main goal of automatically discovering the speech segments of a language, whereas the other one is an intermediate representation towards this ultimate goal. But you can already guess there's a strong connection between these two strands, and actually they can benefit from each other as well. So if you have a good subword discriminative feature representation, this is beneficial to the automatic unit or acoustic unit discovery. Conversely, discovered speech units with good consistency with true phonemes are helpful to learning subword discriminative acoustic feature representations. So these two are closely connected and can help each other. And in this talk, I'm going to present you some work that Simon has been doing on this close connection between UAD and the subword modeling. So the first part is about the benefit of AUD for unsupervised subword modeling. Now, what is unsupervised subword modeling? Well, first of all, it's a non-trivial task because the major difficulty is the separation of the linguistic, phoneme, from non-linguistic, like speaker information. And then, again, also here, there are two main research strands. One is purely unsupervised, and one exploits cross-lingual speech and text resources. So it is partially supervised, but it uses out-of-domain languages. So it doesn't use supervised information from the target language, but only from other languages. Now, the way Simon has been approaching this problem is by combining these two research strands within unsupervised subword modeling. And he has developed a two-stage learning framework. And the first stage is the front end. And it consists of a self-supervised representation learning model. Particularly, it's autoregressive predictive coding, or APC, which is an unsupervised technique. And the nice thing about APC is that it preserves phonetic or subword and speaker information, but at the same time makes it more separable. And that is really interesting because that's actually what we want to do. We want to create acoustic representations that separate out the linguistic from the extra-linguistic information. The second stage is the backend. And the backend consists of a cross-lingual out-of-domain DNN model with a bottleneck layer, a DNN BNF, and which is trained using the APC pre-trained features from the first stage. And this one creates the missing frame labels due to the zero resource assumption. Now, if you look at that in a picture, this is what it looks like. So we have in the training phase, we have our target language, I'm going to talk about that later, about the language Emboshi, so I'm going to use Emboshi as an example here. So we have our untranscribed speech of our target language, say Emboshi. Then we're going to train the APC features in an unsupervised way from that. And then we have the pre-trained APC features. These are used as inputs here in the cross-lingual phone-aware DNN BNF. Now, we also need phone labels in order to train the system. Now, these labels are created by using an out-of-domain ASR. And this out-of-domain ASR is trained using speech of another and transcriptions of another language. Say, for instance, Dutch or Mandarin, which we actually use in our system. So in our first experiments, we used an OOD ASR system that was trained either on Dutch or on Mandarin Chinese to create the phone labels, whereas the features, which are of course based on the target speech, actually came from English. So we had English here as a target language originally. Then the subword discriminative features are actually here taken from the bottleneck layer over here. And then during our testing phase, we have the untranscribed speech of our target language, either English or Emboshi, depending on the experiments. Then we extract the APC features, and then we push them through the DNN BNF, and we get the subword discriminative features out, which we then use as our features in the subsequent tasks. So this is the two-stage that we have. So we have the APC here in the first stage, and we have the actual extraction of the subword discriminative features in the second stage. Now, how is the system trained? So we have English to train. So we have a lot of English data actually. So we use LibRelite we use the Unlab 600, Unlab 6K parts of LibriLite, and we use that for the APC pre-training because English is our training language. So we're using it for the unsupervised pre-training for the APC features, and we use it for DNN BNF model training. And we also use another part of LibriLite Unlab 6K also for DNN BNF model training. So we have a lot of data here that we use to train the DNN BNFs. And then we also have different random subsets from Unlab 600 that are smaller in size. And I'll come to that in the next couple of slides why we have that. Then to train our OOD, the out-of-domain ASR system, we use Mandarin, and specifically the Adadatang database, which is 140 hours of read speech. So this is a system that is used to create the labels from the target, that is used to create the labels for the target language without actually being the target language. In the other experiment, we're using Dutch, so it's spoken Dutch corpus, also again to create the labels for our system. So if we go back, so this particular part here is either trained on Dutch or trained on Mandarin. And the spoken Dutch corpus contains many different speech styles, about 14, and consists of 483 hours of speech. And then we test our system on English, on the def and test parts of LibriLite. For those of you who are not familiar with the connotations, clean here after the development and test set, it means that it is a higher recording quality and has an accent that's closer to US English, so it's slightly different data. And we also, in order to be able to compare the results with the literature, we also compare it to the Zero Speech 2017 data. Now, how do we evaluate how good the system is able to create features that can separate between subwords? For that, we use the ABX subword discriminability measure, which was developed for Zero Speech in 2017. And for those of you who do not know how it works, there are, you have A, B, and X. This is from the name already. And so what I should say is that this particular measure is actually based on human experiments. So ABX task is a very well-known task within psycholinguistics, for instance, where listeners have to determine whether two sounds, so they're hearing two sounds and then that are different, and then they're hearing a third sound, or the X, and they have to determine whether something is similar to the first one or the second sound. So whether it's similar to A or B. And this is the automatic version of that. So we have A, B, and X, which are speech segments, and the size doesn't really matter, they're speech segments. Then we have X and Y, which are different phonemes in that particular language. And then A, so speech segment A is an element of phoneme X, or is part of phoneme X, and speech segment B is part of phoneme Y, and then X, speech segment X is an element of either phoneme X or phoneme Y. So we don't know which phoneme it belongs to. Now, an error occurs if a given predefined distance measure D is, so for instance, if you have a speech segment X belonging to phoneme X, and then the distance between the speech segment A, which belongs to the phoneme X, is larger than the distance from the speech segment X with the speech segment belonging to phoneme B, or vice versa. So we're looking at, you have a speech segment X, we're looking at the distance between these speech segments A or X and B, and we're looking at, so if it's closer to the right phoneme, then it's an okay, otherwise it's an error. The distance measure that is typically used is dynamic time warping, so we also use that. The point here is that, or important here is that A and B belong to the same speaker. There are different versions of the ABX task, but here we're looking at a situation where A and B belong to the same speaker. And then we have within and across speaker evaluations, basically meaning that either X belongs to a different speaker, and A and B still belong to the same speaker, or X belongs to the same speaker, which as A and B, in which case it's a within speaker evaluation. So there are two types of evaluations. Now, we do two types of experiments. Actually, we do one experiment and one analysis. So in the first experiment, we systematically investigate the robustness of our approach to different amounts of training data. So this is the situation where we have a low resource environment. So we wanted to know how little or how much data is needed to be able to train the system that we propose. So how realistic is it to actually use it in a low resource environment? And then we did phoneme level and articulatory feature level analysis. So AF stands for articulatory feature. These analyses. So what we did was we took the ABX task, but then Simon created a slightly different version of that. So he was able to compare at the phoneme and at the articulatory feature level using the same type of ABX metric as I just explained. And then what we want to know was how well is a speech feature representation capable of distinguishing one phoneme from another or one articulatory feature attribute to another. So for those of you who are not familiar with articulatory features, so articulatory features, the way we define it in our research, are the acoustic properties belonging to the articulatory, articulation of sound. So you have, for instance, manner of articulation, you've got place of articulation for consonants and the location of the tongue for your vowels. So these are the results that we had for the first experiment, is that we wanted to know how robust our system is against different amounts of training data. So what you see here is two panels. We have the cross-speaker results and the within speaker. So cross-speaker, the X comes from a different speaker than A and B. Within speaker, the speech segment X came from the same speaker as the speech segments A and B. Then we have the number of hours of training data on the X-axis, and we have the ABX error rate in percentage on the Y-axis. Blue indicates Dutch, red indicates Mandarin, and we compare two different types of inputs to this stage 2. So the proposed APC input, so the stage 1 as proposed in our system, but we also compared it to the standard MFCC approach. So without using the first stage, but just using the MFCC representations as input to the DNN and BNF. Now, what can we see here? Well, first of all, we see that the blue lines are below the red lines almost everywhere. So if we use Dutch labels for in our so if we use Dutch to train our out of the main ASR system to generate the labels to be used to train the DNN BNF, we get better results than when we use the Mandarin to train our OOD ESR system. And this is probably because there's a larger similarity in Dutch than Mandarin with English. Dutch has a phoneme inventory that's closer to English than Mandarin has, and Dutch is a Germanic language like English, and it's a non-tonal language like English, whereas Mandarin is tonal. What we also see here is that generally speaking, we see a slope going down. So with more data, we get an increase in our performance. Then what we see is that when you compare the diamonds with the, how do you call them, the stars, let's call them stars, we see that the diamonds typically are below the stars. So the APC features, so the proposed stage 1, outperforms the standard MFCCs as input to our second stage. Now, interestingly, when you start comparing across the amounts of data, then what we see here is when you compare this particular data point here, the 209 hours, which belongs to Dutch, and then using the APC inputs, this is approximately the same performance as you would get with the MFCC input. So if you, and that's for more than 5,000 hours of speech. So you get the same type of performance, but using vastly different amounts of training data. So you need about, well, the way we phrase it, if you use APC pre-training, it saves you about 96% of your training data to get the same performance. And this is even bigger, this difference for Mandarin. So when you here compare this particular point here, so again, the 5,000 hour point with it's approximately the same performance as the 52 hours for APC training. So APC pre-training saves about 99% of the training data for Mandarin. So it looks like using APC pre-training really helps you for this particular task. Now, how does this compare to the results that we can find in the literature and also to the challenge top line? So top line, so this is the ABX error rates on the zero speech to 2017 English evaluation sets. The models are trained in the same way as I just described. Now here at the bottom, you see the top line. So this is the one that came with the challenge, and number 10 here. I unfortunately can't remember which paper that is. But they had the best performing system so far using OOD data. So in a way similar to what we've been doing, but they actually, so these two systems, top line and number 10 here, they actually used labeled data, whereas in our approach, we don't use any labeled data of the target language. And what we see here is that the best results, our best results here, so this is the 7.00 in bold here for the across speaker and the 4.99 for within speaker, actually outperform both the top line and the best results so far. So this is really, really interesting that this seems to work. So we were interested, so why does this work? So what makes these APC features better than the standard MFCC features? So that's why we looked into the phoneme level and the articulatory feature level analysis. And then when we compare our approach to the MFCC features, we see that there's a large improvement or that they're actually better in capturing diphthong than monophthong information. So our approach is better able to capture the dynamic parts of the phonemes than MFCC features, and they're doing better than capturing the monophthong information. Now, why that is, we know we are not that far yet, but this is what we observe in these analyses. And we also see an improvement in capturing consonant information, but that it varies greatly depending on the consonant. So how much improvement you get from going from MFCCs to APC features, we see an improvement, but how big that jump is depends on the consonant. And what is interesting also for the results that I'm going to present in a few slides from now, there's a positive correlation between the effectiveness of the backend in capturing a target's phonemes information and the quality of cross-lingual phone labels assigned to that target phoneme. So the quality of the labels generated by the OOD ASR are really important in how well the BNF, the DNN BNF features are able to capture the target phonemes information. Now, when we look a bit closer or in more detail at what information is better captured, then we see that, again, comparing the APC features with the MFCC features, that the APC features are better able to capture manner and place of articulation information and vowel height effects information. Basically, all the articulatory feature information are better captured with the APC features. And for manner of articulation, we do see differences in how well sounds or consonants are being captured. So consonant information is being captured. So we see that stop and fricative information is less well captured than affricate, approximate, and nasal information. And for place of articulation, we see that the palatal information is actually best captured. But here we should note that there's only one palatal sound in our data set, which is the year. So it's also possible that these results are somewhat biased by the fact that there's only one palatal consonant in our data set. But here, what we see here is that so the different features are able to capture information about the sounds in a different way, and that some features are better than others, and that some information is captured better than others. And I think this is really important. And if we want to develop better acoustic features that are better able to distinguish between phonemes in a sound, then we need to look at a lower level and find out what the features are able to capture and what not, and where we have to think about maybe trying to improve on our feature representations. So to conclude this part, front-end APC pre-training outperforms a system with only a DNN BNF backends, which uses MFCCs as input. We see in performance increase with increasing amount of training material. And interestingly, we see that the performance of our best system, which is 6,000 hours of untranscribed training data, is very close to that of a supervised system trained on 1,000 hours of transcribed data for target language. So not having any data, but lots of it, or lots of not having any transcriptions, but lots of it, still gets you to a performance that's very close to a system where you do have the transcribed data. And when we compare the outcomes of the phoneme and the articulatory feature level analyses, we see that the articulatory feature information is less language dependent than phoneme information, which is actually in line with the linguistic principles underlying articulatory feature phonemes, where phonemes are language dependent, also the pronunciation is language dependent. Articulatory features are less language dependent than phonemes are. And that's also what we see here, which means articulatory features are better. It's easier to transfer them across languages than phonemes are. So this was one side of the story. Now, the other side of the story is what we're going to talk about next. So this is work that Sion presented last week at Interspeech, and it deals with the benefit of unsupervised subword modeling through AUD. So previously we talked about how the role of the benefit of AUD for unsupervised subword modeling, and now vice versa. Now, acoustic unit discovery, there are two main single-step approaches. So typically this is done in one single step. You have self-supervised learning algorithms, which use a quantization layer to obtain a finite set of discovered acoustic units. And the other method is to use a Bayesian non-parametric versions of HMMs. There are a few combinations of these two. I'm not going to dive into that. The proposal of Sion is to not use a single step, but rather also here use a two-stage learning framework. I have to point out that this is a different two-stage learning framework than the one that I just talked about, although they're both two-stage learning frameworks. Here, he combines unsupervised subword modeling and acoustic unit discovery into this one framework. In the first stage, we learn a frame-level subword discriminative feature representation, so USM, what we just talked about. The second stage applies clustering techniques to the learned frame representations of the first stage to obtain a set of clusters as the discovered acoustic units. So here we're going to first find the acoustic representations that can, as well as possible, distinguish between speech segments. And in the second stage, we're going to apply clustering techniques to these segments in order to find discovered acoustic units. Now, the motivation, I think, kind of speaks for itself. The subword discriminative feature representations can provide a better separation between sounds and spectral features. And compared to an MFCC representation in a subword discriminative representation, what we find is that two examples of the same phoneme are closer together, whereas those of different phonemes are further apart, which is exactly what we want to have. So it's a highly desired property in clustering-based acoustic unit discovery. So how do we do that? First stage, we are going to apply the USM framework that I just talked about in the first experiment. But we have a few changes. So where previously we used either English or Mandarin to train our OOD ASR, here we're using a multilingual OOD ASR. And the reasoning is that different languages have different phoneme inventories. So if you have a multilingual OOD phone label set, so phoneme label sets, you capture more sounds, and yet you basically have a more extensive set of sounds that you can model. So in principle, this should be more useful for acoustic modeling of the target language, because there you can make more fine-grained distinctions between phones in the target language, because you have more labels. And the other difference is that the other difference is that we are going to compare APC versus MFCC features directly here. So no, some difference actually the same. So where we previously had the APC pre-training and we had the MFCs directly going into the DNN BNF, this is the same what we're going to do here. The biggest difference here is the fact that we're using a multilingual OOD. And my apologies. So the second stage, so this was the first stage, which is where we're going to create the feature representations. These feature representations go into the second stage. And in the second stage, we're first going to estimate the phone segment boundaries using an OOD ASR, so multilingual OOD ASR. And then we end up with variable length segments that are, but we need to represent them as fixed dimension vectors. So we're using two different approaches to go from the variable length segments to the fixed dimension vectors. One approach is the average-based approach, and one is the downsampling method. Once we have these fixed dimension vectors, we're going to use k-means to cluster the speech segments and hopefully find our acoustic units. Here we're going to use the target language is Emboshi, which is an actual unwritten language, an actual low resource language. So we're moving away from English to an actual low resource language. We have 3 speakers of Emboshi, just over 5,000 sentences and 4.5 hours of speech. For the training of the OOD ASR, we have 13 phonetically diverse languages. 5 languages are from the global phone data set, and we have 8 Yapa Babel languages. Yeah, the details of what languages you can find in the paper, but basically we have a bunch of European languages, so Romance, Germanic languages, and we have from the Babel languages, we have an African language, we have several languages from Asia and specifically Southeast Asia. So rather different languages from across the world. Now we're going to evaluate our system using the normalized mutual information, or NMI. And the NMI determines the statistical dependency between the discovered units and the ground truth phone units, which is computed based on the frame level confusion matrix. So we want to know how well the discovered units match onto the ground truth phone units. And the higher the NMI, the better it is. We're also going to look at the accuracy of the phoneme segmentation, and we're going to have a tolerance window of plus and minus 20 milliseconds of where the phoneme boundary is placed compared to the ground truth phoneme boundary. Also here, the higher is better. And I'm going to present you the results of the stage 1 and stage 2 experiments, or evaluation, and then the final results. I don't know how I'm doing on time.
So another 5 minutes, Odette, okay. And then we can take some
perfect.
questions.
Great. Yes, perfect. So the stage 1, what we find is that the MFCC features actually outperform the APC features, and this contrasts the earlier results. Because if you remember, the APC there did a lot better on the than the MFCC's features. But there are 2 main and I think important differences here. The first one was that previously we were looking at the USM task. So the unsupervised subword modeling task, whereas here we're evaluating on the acoustic unit discovery task. So 2 different tasks. Also, previously the APC was trained on the target language, which was English, and eventually was also tested on English. Whereas here we're using the same APC model from the previous experiments, so trained on English. Whereas we're actually testing on Emboshi. So there's a language mismatch here. So that's probably the reason why, or part of the reason why the MFCCs are now outperforming the APC features. The second stage, we were interested in the average-based versus downsampling method to create the fixed dimension vectors, and we found that the average-based were equal to or slightly outperforming the downsampling method to create the fixed dimension vectors. So that's what we used in our final system. So we used MFCC features, and we used in our first stage, in our second stage, prior to clustering, we used the average-based method to create the fixed dimension vectors. And here are the final results of our best model. So we looked at different number of clusters in our k-means. So we had 30, 40, up to 70. And then in the second row here, we see the NMI score. And here we see, in the bottom row, we see the F score for the phoneme segmentations. What we see then is that in bold, we see the best results. For the NMI, the number of clusters is between 60 and 70 gives us the best results for the AUD task. And when we look at the phoneme segmentation boundaries, then we see that it is less sensitive to the number of clusters of NMI. So the range here in the second row is larger than the range of results that we see here for the F score. And the best model is with clusters between 50 and 70 clusters. So around this area. Now, when we then compare the AUD, so the found units, and we compare that to the gold standard, we see that there's about a 16% performance gap between the gold standard and our system. And analysis show that this is due to imperfect phone boundary information. So if you want to improve the system, then possible improvements are to improve the phone boundary estimation and possibly adapt an interactive approach, refining segmentation, type of language, acoustic modeling in a way. So this is where we hopefully will be able to look into the future. Now, to conclude this part of the presentation, actually, no, this is the conclusion of the entire presentation. Sorry. So the acoustic unit discovery benefits unsupervised subword modeling by providing pseudo phoneme-like unit labels. So we can create better feature representations if we know where the phoneme boundaries are, and we can get that if we have the acoustic unit discovery labels. Vice versa, unsupervised subword modeling benefits acoustic unit discovery by providing a better separation between sounds and spectral features. So if we have features that are better able to separate out different sounds and keep the close segments that are from the same phoneme, then we eventually get better discovered units. And our two-stage frameworks, the one for USM and one for AUD, both show state-of-the-art performance on the USM and AUD tasks separately. The take-home message: for many languages, conventional supervised acoustic modeling cannot be applied directly, simply because we do not have enough transcribed speech materials. We can apply unsupervised acoustic modeling there, and we can determine the sounds of a language without any linguistic or textual resources. Results are getting better, but we still have a long way to go, unfortunately. And that's it for now. Thank you very much for your attention, and I'm happy to answer any questions I can.
Thanks so much, Odette, for a really nice talk. So it's time for questions. Please put your questions down in the chat box, or you can unmute yourself and ask Odette your question.
Oh, here it is. Oh, there's a question. Oh, wait, my mouse here. So what if training data contains noise? Will it affect performance? Yes, that will definitely affect the performance, because if there's noise present, then the speech segments will differ even more than they will normally already differ based on their pronunciation. So it will be even harder to find clusters, find the right clusters of the speech segments. So yeah, I think that it will definitely play a role. But I don't think we actually have done those experiments. It would be very interesting to see what happens. Because on the other hand, reasoning the other way around, if the training data, especially if the APC pre-training contains noise, it might well be that it will actually help to get more abstract representations of the speech signal, which then can be beneficial in training of the bottleneck features. So yeah, I can reason both ways. So I think this just calls for an experiment. So thank you very much for that suggestion and the question.
Okay, are there any other questions?
What challenges do you foresee in unsupervised acoustic modeling for disordered speech? Oh, that's an absolutely brilliant question. I think that's going to be really, really hard. So we're currently working on experiments with disordered speech, mostly focusing on voice conversion, but also on automatic speech recognition of disordered speech. And what we see there is that there's the way sounds are being produced are so vastly different from how typical speech is being produced, and differ between people as well. It's going to be really, really hard to do any unsupervised acoustic modeling, in my opinion, because the variance, if you look within one, the pronunciation of one phone, you already see such a wide variance in types of pronunciation. So I think it's going to be really, really hard to do that, to do unsupervised acoustic modeling for disordered speech. Another question is, what if audio contains multiple speakers and speaking at the same time? My guess would be that would be harder. So if multiple speakers means people speaking one after the other, that's fine, because that's also what we're currently using for training to do the APC pre-training. But people speaking at the same time, then things become really hard, because it becomes harder to what then is a sound, right? So I think if you have overlapping speech, it will start to deteriorate the performance. But with multiple speakers, I don't see a problem.
So Odette, I had a quick question. In your slide where you showed the plots for with using Dutch and Mandarin, it was interesting to see that the gap between performance when you're using MFCC features and the APC features for Dutch in the same speaker, the within speaker setting, it was much smaller.
Yeah, that's true. You mean this difference here?
Yeah,
smaller than the difference over here. Yes.
Just across the board. Yeah, it's much smaller. So is that you mentioned that the APC features are better at kind of disentangling content and speaker information.
Yeah.
But it doesn't exhibit this property when you move to Mandarin, though. So I was just curious if you had any thoughts on why you're seeing this for Dutch.
It's a good question. Just thinking out loud, which could be wrong, of course, is that for Mandarin, we have one type of speech. It's only written speech. Whereas for Dutch, we have all kinds of speaking styles. And so it might be that Dutch system is simply a bit more robust. It's better able to abstract away across different variants of different types of pronunciations, and that one way or another can influence these results.
I see. Okay. Yeah.
That would be my guess, but yeah, I wouldn't know for sure. Absolutely not.
Thanks. Yeah. Are there any other questions?
Well, I have a quick one. Similar to this one, when you do the analysis on APC features with the articulatory features, I mean, as the author of APC, I'm flattered. Yuan is here as well, so I won't put him on the spot. But when you're looking at the analysis, do you see any weakness that APC cannot identify? For example, I remember that you have, one bullet, when you have, I've seen you have one bullet point talking about approximate nasals, maybe? Yeah, and it seems like these group of phonemes are voiced, and somehow the unvoiced ones are not.
No, that's not the case.
That's not the case. Okay.
No. So stops, fricatives, approximants, and also nasals all can be both voiced and unvoiced. So that's not the difference. So I would say no. So stops and fricatives tend to have frication, so a bit of noise in there, but the affricates have that as well. So on the one hand, apparently stops and fricatives are less well captured. So if affricates would have been part of that group, then I would have, it could have been that the frication is not that well captured, but since affricates are actually better captured than stops and fricatives, I don't think it's the frication. So I don't have the results at the front of my head right now. So I think we have in the paper we have some numbers or figures showing the results of the analysis. But there is nothing. It's definitely not voicing that is a problem here, because stops and fricatives and all of them can be both. Well, nasals typically are voiced. Approximants are typically voiced as well, but stops and fricatives and affricates can be both voiced and voiceless. So no, I don't think it's voicing. That's the issue here.
Okay.
Yeah, I can't say more about that right now.
Okay, I think if there are no further questions, okay, there's one question.
Yes. Could it be another case of capturing dynamic aspects as well? Affricate release, slow nasal onset offset. Yeah, I was thinking about that when I was looking at that, but I'm not entirely sure whether it's the dynamic part, because stops are highly dynamic. You have a closure phase, and then there is this release. So stops are, I would say, the most dynamic consonants that we have, whereas fricatives tend to be very stable. This is just a frication over time. Affricates, again, are quite dynamic because they contain because you can view them as a very short stop followed by a very short fricative. And approximants, depending on which one it is, can be more or less dynamic. So I don't think this is related to dynamics, but it is a very interesting way of looking at it, and maybe we should have a closer look at that. So thank you for that suggestion.
Okay, great. I think those are all the questions. Let's thank our speaker again. Odette, thanks so much for taking this time.
Thank you for having me here.
About this work. So Hao, over to you if you want to make some announcements before the poster session.
Yeah, I think we'll just take a quick break, and then, during the breaks, if you want to head over to Gather Town, feel free to do so. And if you are paper authors, if you're prepared, feel free to present your posters there. And then we'll have a little bit over an hour of poster sessions, and then we'll have a quick break as well. And then we'll come back at, let's see, 5 p.m. UTC +0 for the next talk. All right, so see you guys.
to speech recordings. But the challenge there is that when we do this, it's capped here, and then we have a label